This video is the last in a series on the practice of controlled drainage. In the previous video, we looked at an example design, and in this video, we'll discuss the operation and management of controlled drainage systems. The learning objective for this video is to be able to understand, discuss, and give examples of different management scenarios for controlled drainage. In developing a management plan for controlled drainage, we're trying to balance three things: the environmental goals for the system, the crop production goals for the system, and then the individual site characteristics of the field. So, coming back to the golden rule of drainage, the goal should be to manage the system to only drain what is necessary to support crop production and to limit nitrate loss. So there are two main questions we're trying to answer when we're developing a management plan for controlled drainage. The first is when to raise and lower the outlet, and the second, then, is what height should the stop logs be set at. In developing a management plan, it's best to use an adaptive management framework where first we develop a plan, we execute that plan, and then we evaluate and learn how the system functions, which then allows us to make any adjustments to improve the operation of the system, and we then continue to refine the plan. In doing that, ideally, we'd monitor precipitation and water table response with one or more water monitoring wells. This allows us to be able to learn how the system responds to different events, how quickly it responds to system changes, and then we can use that to adapt as needed. So let's start with the most conventional management scenario. We have three different management modes. First is winter conservation mode, where the stop logs are added to raise the outlet to within 6 inches to 1 foot below the soil surface to hold as much water and nitrate back during the non-growing season, while still allowing a little room for infiltration. The next is summer conservation mode, where the outlet is raised to balance conserving water for crop water use and nitrate loss reduction with preventing crop damage from excess water. The outlet level chosen will depend on crop and soils, but may often be somewhere between 18 inches to 3 feet below the soil surface. And then finally, we've got conventional drainage mode for when full drainage is needed for field operations and to encourage root development. So if we look at how that plays out through the year, this is our soil surface and the root zone down to the drain pipe. We start the year with the outlet raised up near the soil surface in winter conservation mode. Then, a few weeks to a month before spring field operations are expected to begin, the outlet is lowered to drain the system to make the field trafficable for timely field operations. The system is left in conventional drainage mode long enough to encourage good root development, and then the outlet is raised in summer conservation mode. In the fall, depending on conditions, the outlet can be lowered again to dry the field out for timely harvest, or if it's a dry fall, we may not need to change the outlet at all. Then once harvest is completed, the outlet is raised back to winter conservation mode. So we've got potential drain flow reduction from winter conservation mode and potential conserved water as well as drain flow reduction from summer conservation mode. As we discussed in the introduction video, though, controlled drainage only controls the outlet elevation. So although we have these control structure settings, the actual water table height will still depend on precipitation and evapotranspiration. For example, on poorly drained soils, in most years, we begin the season with a shallow water table necessitating drainage. After the outlet is raised again, it takes timely rainfall to be able to raise the water table again. And it's possible that large events may raise the water table higher than desired, so that the outlet needs to be lowered again temporarily to prevent crop damage from excess water. Then in most years, evapotranspiration will begin to outpace precipitation in the summer, and the water table will drop. The water table may stay below the drains until the crop senesces and precipitation exceeds ET again in the fall. Now let's look at some alternative management scenarios. An alternative for producers who are willing to implement controlled drainage for the water quality benefits of reducing drainage during the non-growing season but are risk averse about raising the outlet during the growing season. In this case, the system can be operated with no growing season management. At the other end of the spectrum is a management plan that aggressively tries to conserve as much water as possible. The outlet can be adjusted multiple times as the crop root zone develops. In this case, there's more risk of crop damage from excess water, and there is a risk of limiting root development if the water table remains shallow, which can leave the crop susceptible later in the season to drought stress. If this management scenario is used, an aggressive strategy takes active and frequent management to prevent crop damage. In far northern climates, like northern Minnesota, North Dakota, and up into Canada, it's often recommended to remove the stop logs over the non-growing season to prevent control structure freeze-up, which can delay drainage in the spring until the structure thaws. If cover crops are part of the cropping system, instead of winter conservation mode with the outlet within a foot of the soil surface, a lower outlet elevation is used to limit damage to the cover crop and allow for more growth of that cover crop. If temporary seasonal wetland habitat is one of the goals of the system, then the outlet is raised high enough so that depressional areas are ponded to create that wetland habitat. Finally, if sub-irrigation is used in combination with controlled drainage, then controlled drainage can be used to hold water while the water table is above the drain lines. And as the water table drops, water can be added back to the system to maintain a favorable water table level. So that wraps up this series on controlled drainage, and hopefully now you have an understanding of how controlled drainage can be used to provide added management to the drainage system to address environmental and production goals.